some questions that are very like intuitive that I'm like that I don't really understand. So
Got it.
yeah, I'm glad I went over it
Yeah.
or went through it. So yeah, today I want to go over a passage from there and maybe like two additional discretes
Okay.
here. Okay. I can get started.
Uh, yeah.
What's
Yeah.
up?
Yeah. Go for it.
Okay. Retroreflecting arrays consist of spherical beads. Light is refracted as it enters the bead, then reflected off the back of the bead. Okay. Arrays of retroreflectors are attached with flexible sheets used as safety reflectors on clothing and bicycles. Ideal retroreflectors return a beam to its source regardless of the angle of incidence of the beam to it.
Yeah.
So, like, what I'm trying to understand, basically, are they talking about just like stuff that, just like reflective stuff in the dark, for example, when like, there's like a biker and the biker has like reflective stuff on the bike, and if a car shines a light, it reflects off.
Uh-huh.
Mhm. Ideal retroreflectors return a beam to its source regardless of the angle of incidence of the beam to it. Each light ray is returned on a path no farther from the diameter of a bead from the source ray. Thus, if a distortion that changes the path of light is placed in front of the retroreflecting array, the incident and the reflected rays will pass through the same distortion. When this occurs, the ray perfectly retraces itself, thereby canceling the distortion. I don't really know what I'm reading, like fully.
It's okay. Continue.
Okay. An experiment is conducted with the setup illustrated in Figure 1. A light source covered by a screen with a pinhole. Okay. In it provides a point source of light. A glass pane acts as a beam splitter. Yeah. Some
Okay.
of the source light is reflected out of the experiment. The remainder of the light is incident upon the array. Source reflected out of the experiment. Okay. Remainder of the light is incident upon the array. Some of the light returning from the array is reflected at a right angle to a viewing screen by the beam splitter. The wavefront reflected from retroreflecting array will be irregular. However, a pinhole image will still appear on the screen because the human eye cannot perceive separation of the wavefronts.
All right, let's see if we can make sense of this figure here. So we have a light source screen with a pinhole to make a point source of light. Um, a glass pane acts as a beam splitter. Some of the source light is reflected out of the experiment. So you can see that happening where?
Here,
So the
like
light
the down arrow.
it's here, yeah, and then some of it gets reflected like that. The remainder of the light goes through and hits that array, the
Mhm.
reflector array. Um, some of the light returning from the array, so some of that returns here, gets reflected at a right angle to a viewing screen, so that gets reflected this way to the viewing screen. Uh,
Mhm.
the wavefront reflected from a retro reflecting array will be irregular. Um, However, a pinhole image will still appear on the screen because the human eye cannot perceive the separation of the wavefronts. So, okay. Um, it could help to think of this or to draw this as a from like a bird's eye view.
Hmm.
So if this is our beam splitter and this is our incident light ray, it would, I believe it would, yeah, would cause it to reflect at a 90-degree angle. Um, and when this one happens, they definitely say that it's at a right angle. So I think that can help us. Um, does it make sense though, what I drew?
Kinda. Okay, I mean, I know, like, yeah, kinda.
Because in this drawing here, we see like, the light ray hitting this glass pane, which is at an angle, and it produces this reflected light ray, and you can see that the angle is a right angle, right?
Hmm.
And here there's a right angle too from the figure, but also they tell us it's a right angle. So I just drew a bird's eye view with this being the glass pane, and you can see that, this is the incident light ray, this is the reflected one, and then this is the reflected from the retroreflector array, and then producing this 90-degree angle that hits that viewing screen, right?
Hmm.
So yeah, so I think that can help us drawing it
Okay.
like. Um, so all right, all the other stuff uh seems to be just kind of saying like either if a distortion happens, um something can fix it in terms of this retroreflecting array, but also that when you do the beam splitter, wavefront is irregular, but our eyes can't perceive the separation of the wavefronts. So yeah, I guess they can ask us questions about that. But so far, I think just understanding this figure is the most important thing. Um, so okay, let's try this question out. The beam splitter in figure one is set at what angle to the incident beam?
It's easy after your picture. It's gonna be 45. Yeah.
Yeah.
Okay.
Yep. So yeah, so drawing this really helps, especially because the drawing is supposed to be like three-dimensional, right?
Mhm.
And but drawing like a screen or a piece of paper is two dimensions, so it's hard to kind of perceive something that's supposed to be 3D in a two-dimensional drawing. So that's why I drew the bird's eye view to help me with that. But okay, yeah, I guess 45 degrees then, right?
Mhm.
Okay. Ooh.
So, um,
So yeah, I guess they did mention beads, spherical beads. Um, Interesting.
Yeah, so I got this one right, but I s- I don't know. So the answer is C. I just felt like when we just draw like any surface, light is coming in, and index of refraction is greater of the bead. So low to high angle is going to be bending towards. So it's gonna be like this.
Okay.
And so like yeah, um I just felt like C made the most sense, you know what I mean? Like it's
Well, okay, let's see, right? So what you drew is true. Um, so what we can see is that, well, what we want to see is if we have convergence or divergence. So C has the light ray converging. B has the light ray diverging.
mhm,
A seems to be neither, right?
mhm.
And D seems to also be neither, but for some reason, light hitting it and exiting it is at a slanted angle. So, um, yeah. So yeah, I guess yeah, it'll be C.
How do you know it's converging though?
Well, you see that this light ray, oops, like comes at this single point, and
No,
this.
no, but how do you know that like the answer to it would have to be something that's converging?
So, well, we know that a, for instance, a convex lens is converging, right?
Hmm.
And this spherical bead. So, by the way, like convex, concave, these are in under the broader category of spherical lenses or spherical mirrors because, and that's why they have, you know how like the 2f is the radius of curvature.
Hmm.
So like that's like if you have two of these spheres that are non-overlapping, this becomes the diverging lens. But if you have the two spheres that are overlapping, this becomes the converging lens, the convex shape. So I know that for a lens, a convex shape produces a converging, like causes the light rays to converge. Um, so that's, oh, and then these are spherical beads, which are essentially like a version, like it's essentially like a convergent, like a convex shape. It's closer to being a convex shape than uh concave shape, right? But
Hmm.
I think in addition to that, your reasoning of light is entering into a denser medium would move towards that normal. So like if this is the interface, the region between the interfaces, and let's say this is like the right angle, it should move towards that normal, that right angle. So your reasoning works as well. Um,
Hmm.
so yeah, we have, yeah, both of those would help. Yeah. Let's see, they're drawing. Oh yeah. So like yeah, if this is your interface, this is your normal, you're gonna have the light ray approach closer to the normal. So your reasoning is sufficient.
Hmm. Okay. This I had no idea about. Glass is used as beam splitters replace glass that is identical, except that it has 10% higher index of refraction, which the following occur to the pinhole image.
Has a higher index of refraction, which would mean that the refracted light rays would move so okay, if it's a higher index of refraction, it will refract more, which means it'll move closer to the normal. So how would that change the pinhole image? Um, wouldn't it just be like that previous question?
I don't know. So 10% higher index of refraction.
Yeah, we're
Yeah,
having
but they're trying to make us conceptualize like so the pinhole image is that what's on the viewing screen or yeah, pinhole image is on the screen.
Mhm.
So here's the thing. We have a higher index of refraction, which means it's going to be move even more towards the normal. So it converges more, right?
Mhm.
If it converges more, does that mean it's going to become more clear?
No, I mean so if something's blurry, it means that the light rays are not converging at the same point. Um, Larger or smaller have to do with, you know, the optic stuff that we talked about previously, like where the object distance is and the
Yeah.
distances. But if we're increasing the index of refraction, we should have it kind of like so that drawing that was there before where this goes and hits that. This is the interface, this is the normal, and it moves towards it like this. And wherever this is could be the location of that pinhole image. So if it refracted it more, it should move that pinhole image to be like the location of that pinhole image. It won't change the size, and it because we don't have a change in object distance or anything like that, and it won't make it more clear because that happens if you focus all the light rays at a single point rather than kind of like around a point. So that wouldn't change. The only thing that we're changing is index of refraction, which means that we're changing the refracted rays angle of refraction to be closer to the normal. So, you know, basically, if you just go back to that previous question for a sec. So, yeah. So basically, if you had a higher index of refraction, it would be like there, right?
Yeah.
Compared to the yellow arrow, which has a higher angle of refraction. The blue one that I just drew has a smaller angle of refraction because it's closer to the normal, and you can see that that produces the pinhole image here rather than there. You're gonna just move that image, the location of that image.
Mhm.
Okay.
No, yeah, I guessed on this. I don't know why it says I got it right, but okay.
that,
What?
oh yeah, so they're saying that larger index of refraction, light bends more toward the normal. If you change that, yes, yeah, pretty much. Oh yeah. So what is this question asking us?
So, ask basically, I first thing I did was think about calculating the wavelength.
It's a weird question. So there are no units, because I guess they're asking about the number of wavelengths of light, right?
Right.
So, okay.
So,
Yeah.
I mean, the first thing I would do is find the wavelength just by doing V equals F times lambda. And then once I would get the lambda is where I would get stuck. And I would just be like, okay, time to flag and move on. But
Okay.
okay, but for real though, I think after you mentioned the units, actually, we could use that to our advantage, right? Because if we find the wavelength, then we'd probably just have to divide because the wavelength is meters, and we just divide that by the diameter or the diameter by meters. That's where it's a little tricky, but
Yeah, I'm trying to think about how the diameter plays a role here. Um, let's see. The passage said that each light ray is returned on a path no farther than the diameter of a bead from the source ray. What can that mean? So, wouldn't that mean that the light ray can travel a distance smaller than the diameter? Is that right? Is that's what it's saying, right?
yeah, yeah.
So the distance that the light ray travels must be smaller than that, right?
Hmm.
Okay. Um, okay. So you can okay, okay. Makes sense. So that can give us the distance that the light travels, and once you find the wavelength, you can divide it by that distance to figure out, or divide the distance by the wavelength to figure out how many waves. So they're asking approximate number of wavelengths, which essentially means the number of waves. So
Hmm.
yeah. So you can solve for your wavelength and you can divide it. You could divide the diameter by the wavelength to figure out how many wavelengths can encompass that area, that length.
Got it.
So yeah, go for it.
I mean, okay.
Where are you getting? What is that? Oh, sorry.
What?
Sorry. My bad.
Oh, okay. I was a little scared. I mean, it would be like 1 point something times 10 to the second. Then yeah, what B, I guess.
Yeah, so let me help you with the math here. So, whoops.
Hmm.
5/3. Do it like this. So 3 goes into 5 how many times? Once, with a remainder 2. You take the remainder, you make it the numerator of fraction with the same denominator.
Oh,
Like,
0.666.
yep, got it.
Okay. Okay.
They could have had a choice, like if they wanted to, or yeah, if they wanted to, they could have made one of these choices 3 times 10 to the -7, right?
Hmm.
Because that would make someone, because that would be an easy, like most people who would read this would just be like, all right, they're asking for the wavelength, plug and chug, and then they can choose that.
Yeah, I put D, which was the inverse. So it was wavelength divided by diameter.
I see. Yeah, that can also
Yeah.
be a thing. But yeah, number of waves, essentially.
I mean, is there really any central takeaway that I can apply from this to other problems? I haven't really seen a problem like this asked, but
So first of all, making sure that we know what they're asking for. So they're asking for the number of wavelengths. They're not asking for the number, or they're not asking for the wavelength. That's one. Two, what do we do with diameter? On its own, that has nothing to do with anything. But the passage says that the light ray travels no farther than the diameter. And so using passage information, we can deduce that the diameter can be the maximum distance that light travels. And then when we find, yeah, so essentially making sure that we understand the questions asking for number of wavelengths, not the wavelength. So that's reading, closely. And two, this diameter value doesn't have any relevance except if you look at the passage, and then the passage information would help us see the diameter as the distance that the light travels.
And how about the previous one? That like, I mean, I know low to high index of refraction bends towards normal. Um,
So first, I could probably do so okay, so I'll give you two kind of takeaways here. So one, if we just look at the choices, we can see that okay, if it's clear or not, or opposite of clear would be blurry, would be like if you had like let me better. Like let's say that you had the light rays not all focused at the same point, that's going to produce a blurry picture.
Mhm.
So, and whether it's the image is larger or smaller all depends on object distance. Clear depends on, light rays focusing at the same point. So we know that what they're telling us is that the only thing that we're changing is the index of refraction. We're changing the index of refraction. What does that change? It changes the velocity of the light that travels through it, which also means it changes the angle of refraction. If it's a higher index of refraction, the angle of refraction goes down because it moves towards the normal. And if it moves towards the normal, it again, it won't change anything about the size of the image, and it won't make the image more clear. It just makes the light rays um, bend closer to the normal, which would result in the pinhole image moving.
Mhm.
So you could do that with, yeah, process of elimination first, and then asking yourself, if we change the index of refraction, what else would change?
Okay. Next is this. Sound of a known frequency, wavelength, intensity, and speed travel through air and bounce off an imperfect reflector which is moving towards the source. Which of the following properties of sound remains the same before and after reflection?
Interesting. Okay. Frequency, wavelength, intensity, speed travels through the air, bounces off an imperfect reflector. Okay. Um, my I'm imagining imperfect reflector is something that doesn't completely reflect it, but well, even if it was okay, so walk me through these choices.
Okay, the thing is I have sometimes a difficult time trying to differentiate between sound and light. I know um sound is like sound, first of all, moves faster through solids, fastest through solids, then liquids, then gases. Okay. Sound also, when it goes from one medium to another, the frequency, it stays the same with sound. Um, so now I I guess forgot when I was doing this, but sound when it bounces off of something, um, I guess some of the sound gets like attenuated or whatever. So I mean, look, with between these choices, like I would eliminate C off the bat because I feel like frequency doesn't change. And now speed I'd probably eliminate. And that'd be between intensity and wavelength. But like if speed changes, that probably um I'm saying hold on. Frequency stays the same. So yeah.
Okay, couple of things. Um, do you remember what a longitudinal wave was?
Yeah, it's a sound wave.
I mean, a sound wave is an example of a longitudinal wave, but what is a longitudinal wave?
It's when it's travels like parallel to like each successive wave is parallel to itself. I don't know how to really explain it.
So, so let's say so sound can have expansions and compressions, right?
Yeah.
So let's say that my hands are the expansion and compression, in a horizontal fashion, right?
Yeah.
So this must be in the same dimension, or as you said, parallel to the direction that the wave itself is traveling,
Mhm.
right? Whereas, what's the other type of wave?
Transverse.
So if your transverse wave is moving left to right, it would have to move the medium perpendicularly to it. So if the wave is going up and down, it would move the wave itself would move left or right,
Mhm.
right?
I guess.
So meaning if a wave is going this way, it'll push the medium perpendicularly to it, which is why you'll see this type of thing, like a sine curve,
Mhm.
right? Whereas, let's say these are the air molecules close together, compressing. These are the air molecules expanding, and this is the direction of the wave. You could see that the medium can be compressing or expanding parallel or in the same dimension as the direction that the wave is traveling, right?
Wait, so is a light wave that's transverse, is that perpendicular and parallel?
No, no, no. So if it's parallel, it's longitudinal, like this, because you see this expansion is parallel to the direction of the wave's velocity. And then this compression is also parallel to the direction that the wave is traveling.
Well,
However, for a transverse wave, you could either have it going up like this to push the medium up, or down to push the medium down. But it's still, no matter what, 90 degrees to the direction that the wave is traveling, which is left to right.
mhm.
Okay. So, so again, a longitudinal wave means that the medium at which through which the wave is traveling gets either pushed or pulled in the same dimension or parallel to the direction that the wave is traveling. Kind of like an accordion.
Mhm.
Imagine like an accordion, because an accordion goes, expands and contracts like, horizontally, right?
Mhm.
So imagine an accordion moving horizontally with the expansions and contractions also being horizontal.
Yeah.
Whereas a transverse wave is more like if you drop a pebble into water, right? The wave will move in a certain direction, but the ripples that you see in the water are perpendicular to the
Mhm.
direction that the wave is traveling, right?
Mhm.
That makes sense.
Yeah.
So, yeah, you
So
want,
as you're going like in a longitudinal wave, it goes like that.
yeah,
So, but it's just continuously compressing and expanding.
yeah.
But like when you're going transverse, it's like I can't conceptualize that as well, but like
No, you did a good
I
job. So your arm is the direction it's traveling in, but the medium is going up and down, which is what your hand is doing. Yeah.
guess it might be kind of like that thing where we had the paper and it's like you draw
Yeah.
or
Uh-huh.
you just yeah, you draw. It's like you move your thing up and down and then you just yeah.
Mm-hmm. So, um, that part makes sense.
Yeah.
Okay. Now, so yeah, sound is a longitudinal, light is a transverse. Now, another difference is if a medium becomes denser, light travels more slowly because light travels fastest when you don't have a medium, like in a vacuum. Whereas sound, since sound requires a medium, the denser that medium is, the faster that sound will travel. So that's why, you know, gas, sound will travel faster through solids compared to liquids and faster through liquids compared to gases, right? So that's another thing. Now, what you said about the frequency staying the same, that is only going to be true for light because the energy of a photon, is hf. Planck's constant is something that is only relevant to light. Okay.
Mhm.
So frequency always staying the same, regardless of what medium you're entering into, is a property of light. Okay. Now,
Yeah.
even if, actually, even if they were talking about light here, it still wouldn't be frequency because frequency stays the same for light as you enter into a different medium. But this is reflection, right? Which means that it's not entering into that medium, right?
Mhm.
Now, they do say it's an imperfect reflector. So what that would mean is it's not 100% reflected, which means that some percent of it is absorbed, right?
Yeah.
And if some of it is absorbed, right, it would uh mean energy is lost. And if energy is lost, so um what can you tell me about intensity?
Intensity is not related to velocity, frequency, or wavelength. Um, Intensity can be related to amplitude. Uh, Intensity for light is the amount of photons, or proportional to that.
Uh-huh.
Intensity, I think you said before, intensity is related to amount of sound waves, but I'm not sure that is. Is that true?
That's true, that's true. And also the unit for intensity.
Um, Hold on. I always miss this one. It's just annoying because I've looked over the formula many times.
Yeah, think
Is
about
it power over area?
correct.
Okay, good. So it's joules. Wait, wait. Watts
Huh?
over m squared.
Good. So power over area, and if power is energy over time, an imperfect reflector would cause some energy to be lost, right? So if energy is changed, intensity would change, right?
Yeah.
So,
But
uh,
we're talking about sound here.
uh-huh, yep,
Yeah.
yeah. Um, so yeah, an imperfect reflector would mean it's not 100% reflected, which means some energy is absorbed by that reflector, which means some energy is lost. So the intensity would change. Um, and the frequency, um, I guess would be related to energy. Um, so if some energy is changed or lost, frequency would change. Um, And if frequency changes, wavelength would change as well. But the only thing that wouldn't change would be the speed, because the speed of sound through the air, like that doesn't, it doesn't matter if it bounces off of, if it reflects off of something or not, right?
Wait,
This,
but hold on. You said the frequency would change if the intensity would change, but once again, we're talking. If you said if the energy changes, frequency changes. You said that, right?
yeah,
But we're talking about sound here. Isn't E equals HF for light?
that's for light. Um, and light is when you don't have a change in that frequency, right?
Yeah.
So, but sound, like, so frequency will still be related to energy, but in a sound wave, the frequency does not have to stay the same the way that it would for um light, right?
And I'm also just confused about the frequency. Like, I thought that for sound frequency, oh, it stays the same all the time.
That's so that's going to be only true for light and only true for light as it enters into another medium. So this is not entering into another medium and it's not light. So frequency does not have to stay the same for this.
So wait, when when the sound wave goes from water into air, the frequency doesn't change.
Sorry, so water from water to air, now the medium is changing, right? But if it was light and the medium changes, then yes, frequency does not stay the same. But for sound, if it goes from one medium to the next, the frequency will change. The frequency not changing as you go from one medium to another medium is true for light uh only.
Um, you know what I feel like would work but help best, honestly?
Uh-huh.
If you just told me this and I wrote it down literally, because I think like these types of conceptual problems are just they've always like affected me.
Yep.
And even though this is the pre-15 2015 MCAT, there are many questions that I've encountered
Uh-huh.
about this. Um, so like literally. Um,
So let's not worry about the frequency changing or not changing for this question because we don't have it entering into another medium because it's being reflected.
yeah.
So so yeah, so we can't say that frequency is going to be remaining the same because it's just reflected. So but the speed of something, whether it's light or sound, does depend on the medium through which it travels. And if something is being reflected, it's not entering into a new medium, which means it's in the same medium. And if you're not changing the medium, then the speed of that wave should not change.
Okay. So what if speed does travel into sorry, what if light does travel into a new medium? If the medium is denser, then light will travel slower. For sound, the opposite is true. Right?
Yeah. Mhm.
Okay. Now for frequency, right?
Mhm.
How about for frequency?
Mhm. Um, yeah. So, uh, I would say that think about this for a sec. So, okay. So I think it would actually be, so if you're entering into a new medium, the frequency doesn't change. Now, if I think about, no, so I kind of am thinking about it a little bit more. Um, so V is equal to frequency times lambda. And if wavelength changes and velocity changes, frequency would stay constant. So now I'm thinking about that for sound, and the velocity would change as you enter into the new medium. So what else would change? The wavelength could change. So I'm trying to think if the frequency would change or not. And
Look,
so I think entering a new medium would actually cause the oh yeah, this is a good picture. So you can see the direction of propagation. Yeah.
sorry. Uh-huh.
I think that, oh, okay. Yeah. So the thing that uh I said about frequency unchanging from one medium to the next, I am amending what I'm saying to
Mhm.
matter. It doesn't matter if it's sound or light. Traveling from one medium to another will not change the frequency.
Uh, so frequency doesn't change for either light or sound. Velocity does change, but it's inverse relationship between sound and light. Now intensity. That's one that always gets me. The intensity relationship, I mean, for light, it's just higher pho amount of photons usually corresponds to a higher intensity. If it's a reduced area, so the middle of the day when the sun is shining on a small area, that's a higher intensity. Um, what else?
Yeah, I'm writing some stuff out for you. All right, I wrote light can travel in a vacuum, which is a density of 0, uh, and it is fastest in a vacuum. So the denser the medium is, the slower light will travel in it. Whereas sound requires a medium. You can't have sound in a vacuum. So it is faster the denser the medium gets. Now, intensity for light can be thought of as the number of photons, which corresponds to brightness, and intensity for sound can be thought of as the number of sound waves, which corresponds to loudness. The unit for intensity is watts over square meters. So you can change intensity by changing energy or by changing area. Since speed of the wave depends on the medium, whenever you have a wave changing mediums, you will see a change in speed. This can also change the wave's wavelength, but it will not change frequency. So for an imperfect reflector, since it is imperfect, not all of the wave will be reflected. This means some of the wave is absorbed. If some of the wave is absorbed, the wave has lost energy. Since intensity is power over area and power is energy over time, if we change the energy, we change the power and therefore change the intensity. Since energy changes and frequency is related to energy, this is true for both light and sound, then frequency must change. And also, because we're not entering into a new medium, frequency does not have to stay the same. So yeah, if frequency changes, then the wavelength will change too. But if we are not entering a new medium, the wave speed must stay the same because the wave speed is dependent on the medium. So you could just screenshot that and paste it in.
There's no way you could copy and paste that, right? Like into the Zoom chat.
Yeah, no, I can screenshot it and then paste that in.
You can on the screenshot. Oh.
Yeah. I should have. Oh yeah. Yeah.
So
I should have copy and pasted it. But what you can probably do is use the selection tool and you'd be able to copy and paste it, the text that way. Yeah.
I'll just tell ChatGPT to like write this out.
Oh yeah.
Um, wait. Okay, wait. So are you then amending what you amended and saying that frequency does change?
No, no, no. Frequency does not change if you're changing mediums. Oh,
Yes, 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 yes.
yeah. Um,
Okay.
so if you're changing mediums, then frequency will not change.
Okay.
So that's why here, since we are not entering into a new medium, frequency doesn't have to stay the same. So it'll change because we're changing the energy.
Hmm.
Yeah.
I'm just still like slightly confused about how you know that this happens. Because it's a sound, you know?
Hmm.
So
Yep.
that's the thing I'm confused about.
Oh, okay. Um, yeah. So your frequency, right, will be a factor in the energy of a wave. Now, we're used to seeing that with light waves, with Planck's constant, but it's not going to be that same formula with Planck's constant for sound, but sound still has energy, and that energy will still be related to its frequency. Um, oh, you know what? I thought of a good example. So, you know, harmonic resonance,
Yeah,
where you have the tube and all that stuff.
yeah.
You can change your frequency there, right?
Hmm.
And that can for sound, like, okay, you know how someone like if someone like sings at a certain pitch, they can like cause glass to break,
Hmm.
something like that. That happens because the person's voice is um creating harmonic resonance with the natural uh frequency of glass, let's say, and that can increase that frequency, which can cause an increase in the energy, causing that glass to break. That's kind of
Hmm.
like what you'll see here. So I would just take what I would take away from this is that um or here, I'm gonna write something. Okay. Um, velocity of the wave is equal to the wavelength times frequency. So we have two scenarios. Scenario one, if the wave is entering into the new medium, what first happens is the wave speed changes.
Mhm.
That causes a corresponding change in the wavelength. And that's why you can get your chromatic dispersion where, white light can enter into a prism and then you get the separation by color.
Mhm.
And that's because, like, red light with a larger wavelength refracts less than blue light. So you can see how the wavelength can change and get refracted in a different to a different degree.
Mhm.
Um, but your frequency won't change. Now, that's scenario one. Scenario two, if you have the same medium but energy changes, that means frequency and wavelength must change. But since you're in the same medium, you're not changing mediums, and the velocity of a wave depends on the medium, the velocity of the wave cannot change. So, in other words, scenario one, going from one medium to the next, means that your NV is equal to frequency times wavelength. So if we're changing mediums and velocity depends on medium, we're changing velocity, and we would have to change one more thing here, which would be the wavelength. But if you're in the same medium, your velocity cannot change, which means these would have to change. That's the
Mhm.
fundamental.
And if we're in the same medium, so like these can both be true, right? Technically. Like, so this pertains to yes, when it refracts, but some light will be reflected. But that light that is reflected, change it's a different energy, same speed with different energy.
So the light that is reflected would still have the same properties if this is a perfect reflector. But
Oh.
this part, if energy changes, I should have wrote, but if energy changes, then you would have a change in frequency and wavelength, but not your velocity. That's the key thing here.
Wait, you're saying
Hmm.
if same medium, but if energy changes,
Uh-huh.
what are you saying?
Yeah, if the same, so basically you will never have, sorry. Yeah, so if you have the same medium, you will have the same speed. If you have a different medium, you will have a different speed. That can be, those two things will be always true. So, in the case of a in imperfect reflector, energy changes, and if energy changes and it's the same medium, it means the velocity cannot change, which means it has to be the frequency and wavelength that changes.
Okay. Okay.
I also wrote it like this. Just two questions that you have to ask yourself. Is the medium changing? If the medium is changing, the wavelength and speed change, but frequency stays the same. If the medium is the same, right, then the speed is going to be the same. But if the energy changes, then the frequency and wavelength must change. But what's always going to be true is that changing mediums will have the same habit